Okay. Mm. So I'll begin the things. Okay. So we have finished our chapter 1 things. It is about the introduction of PDE. We have seen some basic definitions, classification, as well as formation of partial differential equation, which is in two types of arbitrary constants as well as arbitrary functions. Also, we have seen some of the classification of solution that is also coming under here. So I will start from there. This is our chapter 2 sections. Okay. So let's begin our chapter 2 with some, I have already started in last week also, but I will go through again as a summary. Okay. So there are some changes I have done in this, module. Okay. So if it is different from your writing, please write down as well. Okay. So kind of. So under the chapter number 2, it is about the classification of first order partial differential equation. Okay. So in that classification of first order partial differential equation can be divided into linear, semi-linear, quasi-linear, and non-linear. They also say semi-linear. Okay. So everything is same. So first of all, we need to know what is linear equations, and it has some divisions of semi-linear and quasi-linear. And if it is not under that, we call it as a so you can see the linear, and linear can be divided into semi-linear and quasi-linear. And if it is not a linear, we call it as a non-linear. So let's see the proper definition first of all. So linear equation we have already seen in our types of equation as well. Anyway, we can see in here, for the first order partial differential equation, which can be written in this way. It may have x, y, z terms. So we know these two are the independent variable. This is a dependent variable, as well as it will be available there. And p comma q. Because of the first order, we can't have r as t, isn't it? So p is our z of x, and q is our z of y. You know, dabba z o dabba x, dabba z o dabba y. We can write in this way also. Okay. So this kind of equation we called as a first order partial differential equation. And if it is linear, it should have the, if it is linear in PQS. So what do you mean by linear? Linear has the powers 1, isn't it? And it should not have any multiplicative of PQ or any, okay, even ZP also not should be. So they say if it is linear, it should have only PQ and X terms, maybe X and Y or something like that. Okay. A first order partial differential equation is known as linear equation if it is linear in P, Q, and X and Y, something like that. Okay. So that is the equation is of the form. If it is this in this form, we called as a linear equations. So I will change the color. Okay. So if this is the proper equation to have the linear equation, which has the capital P, capital Q, R, S are functions. Any the function have the variable x and y. For example, x squared y, something like that. So if and P is our zx plus something, any function of q, any function of z, and any rest of the function which doesn't have the p, q, or z terms. Okay, any something like x squared plus y squared or minus, which has only x and y terms, isn't it? Not the z or not p, q. So this kind of equation we called as a linear equations. So please write down or just modify your things what we have written last week also. So better you start from here, okay? So the classification begin with linear equation. Linear equation can be in the form of this one, okay? So here capital P Q, R as any function. Small p is zx. We know that one already. Small q is zy. So you should show the difference of capital P and small p, q. Okay. Okay, let's see one example for this one. Okay, so for example, the linear equation can be in this way. Please write down this one. Okay, it is. So can be example x squared of p, small p, okay, plus xy squared of q, which is equal to xyz plus x squared by q. Can you see that? This is kind of a linear equation. How? This is a function of x and y, maybe capital P and P, plus xy. This is only the function of x and y, so it can be capital Q. Okay, so this is only with the z we can take this as a r, and these don't have any p, q, z terms, so we can take this as a s. Okay, this kind of equation we called as a linear equation. Okay, what do you think about this one? Second one, let's say p plus q, small p plus q, it is equal to z plus xy. What do you think? Is that a linear? This also linear. Why? Maybe the function, the capital P may be 1, capital Q may be 1, and this also R is 1, and this can be any S. Okay, this is also kind of no need to have all the time there should be any function of x and y. Maybe 1 is also some kind of constant, isn't it? This is a constant coefficient. Here we have a variable coefficient. That's all the things. Okay, so this is also one of the uh, linear equation example. Okay, let's move on to semi-linear or semi-linear. Okay, semi-linear equation. A first order partial differential equation that we know is a function of x, y, z, p comma q is equal to 0, is known as semi-linear equation if it is linear in p and q, and the coefficient of p and q are function of x and y only. They say this is linear only p and q terms only. Okay, what do you think? Maybe other term not maybe requiring the linearity, but these two should obey the linear property. Linear property is what? It should have the power of ones and things, isn't it? So like that. Okay. So that is if the function of the form pxyp qxyq plus rxyz. Okay. So see, earlier we had rx comma y of z into z. Here, this z can be a function of z plus something. No, we don't have nothing. There's no z s terms. Okay. Also, what they are saying is, so something like this. Any p of p, q of q. This side is okay. Same of that one. In this side, maybe x, y, z squared also okay. Okay. So we are only considering P and Q terms should be the linear one. Other terms may be anything. Okay, that can be scared also. Okay, so no need the S terms. Okay, this kind of equation we called as a semi-linear. We know that no half. It only obeying the half of the linearity property. Okay, this half they don't like a linear. You can see the linear one, pxy p plus qxy q, which is equal to rxy. Here also z is a 1 power. Here we don't. Maybe extra s also. Okay, here we don't have, but here it doesn't need to be linear. Okay, that's the only thing. So half of the things, okay. So that's why it says semi. Okay, half. Okay, so let's see one example for that. Semi-linear possible. Okay, let's see x, y, p, small p, okay. X squared by q. These two are having only the function of x and y. The next term may be like what I said to you, maybe z squared or something. Okay, so we don't need the other part. Okay, so this is one of the example for semilinear. Maybe another one, let's say yp plus xq is equal to maybe like this, x squared z squared divided by y squared. Okay, this also, this side not a linearity property, because z has a power of 2, no, but this side it is okay, so we can have that. So sometime this equation can be simplified more, so you can cross product by y squared. You can have y cube p plus xy squared q and x squared z squared. Okay, still obeying the things, no, this side is a linear, this side no need to be, so we say this is as a semi-linear equation. Are you with me? Can you answer me? There are only 49 people there. Can you all understand what I'm meaning? Okay, good. Okay, I'll erase this part. Let me move to the quasi-linear. Okay, this is what I said, like for the semi-linear, I told you like a halfway it is. Okay, quasi-linear like a quarter. Okay, you know, like 1 by 4th. The full linear equation can be 1/4 will be okay. So let's see what it is. First order partial differential equation, this one is known as a quasi-linear equation if it is linear in P and Q. Okay, so there is a small difference here, so you can go through. Okay, they say quasi-linear if it is linear in P and Q. Let's see the definition here. If the equation is the form Pxyp, Qxq, and Rx. So what is the difference between this and this? See the function here, we don't have z. We don't have z here. Here only we have z. But this function can be like, for example, z, p. Okay. Xy, no need to always the thing, no? So anything, cube or something. So this set should be like a semi-linear, but only thing is different between the semi-linear and quasi-linear is these capital P and Z can have any Z's, maybe Z squared. Okay. So they say if it is linear in P and Q only. So P and Q are linear. Okay. So this capital P and Q can be anything. Okay. So I'll show you one example so it will be easier for you. So let's see first example. For example, x squared zt plus y squared zq, which is equal to xy. Okay. You better keep this z also 1. Z also taking here as a independent variable, but it's a function. No? So to keep that linear, better you keep that power as 1. Okay. Okay. This is a quasi linear one. So if you see something z involved in the capital P and small q, you have to have, this is kind of a linear which has quarterly linear. That's we call it as a quasi-linear. Second example may be like this. Let's say I have a function of this one of p plus maybe another function, let's say zx of q, which is equal to maybe another big function. Okay, kind of. So write down these equations. This is x, okay? Okay, so we have seen some ideas of linear, and from that we have seen what is semi-linear and quasi-linear. This is kind of a halfway, this is kind of a quarter way. Okay, so if it is not a linear, we call it as what? If it is not obey any linearity property, we call it as a non-linear, isn't it? We don't need to go through these things. If it is not linear, if it is linear, we have to go through whether it is semi or quasi, okay, or whether just linear. Otherwise, we have to take as a non-linear. Okay, that's the next next definitions. Okay, let me say the definition for non-linear, which is obviously we know, isn't it? So, first order differential equation is which does not come under the above any type of above types. We call it as a non-linear equation. For example, let me see an example of maybe like this. Small p squared q squared is equal to 1 or something. Here, see, our derivative having a power. So it is not in, if it is 1 only, we call it as a linear. It is not obeying that thing. So we take this as a non-linear. Similarly, if it is something multiplied, so this also, even though it is a 1 power, it is multiplied, isn't it? So this is also kind of not a non-linear properties. Okay, it's called as a non-linear. Okay, hope you have understood all about the classification of our first order differential partial differential equations. So let me move to the second heading of these sections. Okay, so which is here our thing is to solve the first order partial differential equations. Okay, so let's see how it is goes. So as I said to you earlier, the first order PDE has the form this one. So I have told you earlier, like f of x, y, z, p comma q is equal to 0. Similarly, for the p comma q is what? You know, isn't it? So f of, if you, let's say you have some more variable, not only x and y. If you have, let's say I have, I mean, a, b, c, these also independent variable. Also, we have the dependent variable z, let's say. Then if you define these derivative, first derivative of, let's say, zx, zy, maybe za, zb, okay? So like that, everything together having one power, no? The derivative will be one power, which is 0. This is also the first order differential equation, isn't it? Okay, this can be taken as p, q. We don't have name for this. That's why they taken like this. Okay, there are 3 dot. It means it continue. No need to be have only 2 independent variable. But you have to know that z should be having, if it is 2 variable, we have x comma y. If you have more variable, we can write this will be depend on other independent variable as well. Okay, that's what it says. Okay, hope you understand that one. So that's why they have written this format little bigger than what I have told you earlier. Okay. Okay, they have taken this as equation number 1. Then they are trying to solve the quasi-linear kind of first order differential equations. Okay. So the general form of the quasi-linear first order differential equation, that's what I said you, like p x y z small p plus q x y z small q is equal to r x y z, isn't it? So that's what we have seen in our classification. Here they have make it little bit easier way. that it is the general form of the quasi-linear they have taken in this way. A is a coefficient. Here they are taking as a function of x, y, and all the variables. Okay. Similarly, A is a function. They are taking A as a function. Like what's capital P, here they are taking A. Okay. This the variable depend on the things what we are doing. So no need to worry. Okay. So A is a function of x, y, z up to whatever the kind, how much you are having the independent variable, that much you can take as a or capital P, anything, okay? Plus into zx, so here P. Similarly, B is also a function, maybe Q, okay? Zy. Each books are taking different variable, no? That's fine. Maybe something like this, which is equal to G, we called as a quasi-linear kind of general form. Okay. So did you understand? It is maybe like this: small p, q, small q. We can make some more also if we having more than, I mean, they are written only for the x and y. If you are having more than variable, we can write some more as well. At last, there's a function of g, okay, or any g, which is known as a general form of the quasi-linear in these sections. We are taking in this way. Okay. Okay. So keep it in your mind. We are taking our quasi-linear first order partial differential equation in this form in our section number 2. Okay. Chapter 2. Okay. So for example, they have given one example kind of equations. We already seen some. Okay. Okay. See here. This is one of the quasi-linear equations. Is that correct? Can you check whether it is correct in our definition? They say Z maybe ZP YQ it is equal to X. Is that obeying our definition of the quasi-linear? Can you answer me, please? So what is our quasi-linear? It should have capital P that has Z also, no? See? Yes. Again, Q. That is also should have XYZ. Maybe can or not. Okay. So here we have only Y. That is also obeying Q. This is P, this is Q, which is equal to R, no? R, X, Y, Z. So anything. Okay. So yeah. Only one person answer me. As the others. Hereafter I will call the registration number. That is easy. Okay. So all should be ready to answer me. Otherwise I will make it as absentees. Okay, so that's fine now. This is a example of the quasi-linear equations. Okay, so they have shown this is the general form. This is one of the example. Okay, now we're gonna see how to solve this. Okay, this kind of equation, how we can solve. So put the next heading. Are you all writing with me? Better you write with me. Okay. So, okay, we're gonna see the techniques how we can solve quasi-linear kind of equations. Okay, to solve the quasi-linear equation that what we have taken, let's say this is a small a, the number, I have changed the number as A, B, C, okay? So find the general solution zx comma y. Our purpose is what? From the PDE, if we solve, we'll get the zx comma y, isn't it? This is equal to something. That's what our solution now. General solutions. Okay. So from this, we will get the solution that x comma y, which is satisfying the given equation. Okay. Find a general solution that x comma y satisfying the given equation of A. Okay. You can write like this. Satisfying the given equation A. Then suppose that is a possible solution to a quasi-linear equation. Then, okay, we know that is a function of, let's say for example, here we taking that is a function of x comma y. Okay. So if it is a solution, we know that total derivative of z should be written as da bar z, let's say I'll write this way, zx into dx plus zy into dy. Or otherwise you can write in this way. This is our total, even though it has two variables. So when you are writing the total derivative, we can't put here dz over dx or dz over dy, no? Am I right? Okay, I'll erase and write again. So what it says is, if it is that is our solution, let's find the solution and equate it. First of all, it is a function of two variable, no? So if you wanted to write the total derivative, you, if it is partially no, okay, our meeting will be end in 10 minutes, so you can join again. Okay, so I'll continue until that. So if you know da bar z over da bar x separately and da bar z over da bar y separately and adding both, okay, that is our total, no? So for that, totally we can write like this. Da bar z can be written as da bar z over da bar x dx. Okay, I'm doing with respect to x first of all, then I'm doing with respect to y. Okay, dy. So this I have I have explained to you in our elementary differential equation already. Okay, so if you substitute this one as zx dx, okay, so this is our zy, no, zy dy. Okay, this is our equation B. This is our equation A. Okay. Are you all writing? So no need to hurry to write all the other thing. Whatever I'm explaining, you write where we are. Okay. And see what I'm explaining. So we have written our A, that is our quasi-linear general equation, as well as our B. Okay, here I think I can stop here. No need to put this one, okay? Because we are only considering x and y. Okay, so you can see from comparing the equation A and B, see this is A zx, here zx dx. This is B zy, this is zy dy. So what you can say? So I can say this A can be, A is a function, no? So I can't write like just like that dx, okay? So I'm just multiplying with one of the unknown constant, okay? Let's write A is a k dx. Similarly, if you equate this term, you have B is equal to k dy. Similarly, the other side, see, this one dz. So G is equal to k dz. I'll tell you why I'm taking this k, okay? Because we are taking A and B as a function of x and y and z also. So we can't just write that, maybe some constant included. So that's why we write in this way, okay? Where you can say k is one of the constant, arbitrary constant or any constant, okay? Okay, from this what you can say, in this equation, only consider this equation. If you take dx divided by a, okay, if you take a down, only remaining is what? 1 over k. This k will be go this way. So, okay, I'm dividing. Similarly, if you take this equation, if you write dy over b, which is equal to, again, what is that? 1 over k. I'm taking same k for everything. Okay. Similarly, dz over g, from this, you have 1 over k again. See here, the thing is why k comes is, our equation is dz is equal to zx dx plus zy dy. Even though I take the k, see here, if I take k, this with k, this with k, if I divide also, nothing happen, no? Am I right? So I'm multiplying by k with both sides. So even it doesn't change anything in this equation now. Okay, we are taking for a reason. Okay, so that's that. So we are having dx over a is equal to 1 over k, dy over b is equal to 1 over k, dz over g is equal to 1 over k. So what you can conclude from this? If you divided dx by a, you are getting the same constant. Let's say k1, 1 over k. I'm going to take 1 over k as any constant of k1. For example, if my k is 2, okay, I can write this one 0.5, no? So like that, okay? So for 1 over k, I'm going to put as k1. Nothing changed, no? See, this one is equal to same half. This one is equal to same half. This one is equal to same half. So what you can conclude from these three equations? Can you tell me in word? I'm waiting for your answer. So for example, if you are taking a is equal to 2, b is equal to 2, any a dash equal to b dash, c dash equal to 2. What you can conclude from here? Let's see your answers. Okay, only one person answered me. 2%. Shall I call your numbers then? Okay. Okay. Let's see who is available. Can you answer me 002? Registration number 002. Can you answer me? Otherwise, I will take you as absentee. If you be quiet. Yes, others also answer me. I'm expecting 002's answer. Yes, all are correct. So it means the registration number 002 is not available. Is that? Okay. I'll take that as absentee. Okay. Let's see. Okay. Yeah, you all are correct. So what is that? If it is all are same value, what do you say? All these are same values, isn't it? All are equal. So likewise, we're going to equate this one. See, dx over a is equal to dy over b is equal to dz over g. Okay, that is equal to 1 over k. That is I can take as a k1. Okay, so this is our equation number 3. So the equation, sorry, it is a c. Okay, not this. The equation c is called, there's a special name for that. Okay, it's called as a auxiliary equation or characteristic equations. Okay, if you are having like this kind of equation, let's say, let's keep until this one. If kind of this equation we called as a auxiliary equation or characteristic equation that you may also heard in ODE. Okay. Okay. Okay, I think we have 2 minutes more to end our session and you can join again. Okay, one more time. Okay, let's see one of the theorem to solve this kind of quasi-linear equations kind. Okay, the general solution of the quasi-linear equation a zx. So we are taking only for two variables. Okay, here the general solution of quasi-linear equation a zx plus b zy is equal to g is given by, this is a solution. General solution can be written as a pi chi is equal to 0. Okay, some books they may use uv. Some books sorry, it's a v. Okay, u and v, or maybe some any variable, but I'm gonna choose pi and chi. Okay, so you know the difference between pi and chi, no? Okay, So this is our general solution. After you solving this, you will get this equation. Okay, where g is an arbitrary function and pi x y z can be a c1 and pi x2 is c2. Our solution of the auxiliary equation, this one. Okay, please write down the theorem and our session will be finished and I will join again. Okay.